In this video, I'm going to go over how to sketch the graph of a rational function that has an oblique or slanted asymptote. Okay, here's your definition. Rational function has the form n of x over d of x, where n and d are polynomials. Denominator cannot be 0. Then you have your general form here, where the degree of the numerator is n, the degree of the denominator is m. And typically, if the degree of the numerator is less than the degree of the denominator, then you're always going to have a horizontal asymptote, and it's going to be the x-axis. Now in my case, I'm going to be looking at the situation where the degree of the numerator is larger, one more than the denominator. In that case, you anticipate a slant or oblique asymptote. First thing you want to make sure that your rational function is in lowest terms. Okay. By definition, you can see generally a rational function is basically a polynomial over a polynomial. 1 over x would be a very basic one. Okay. So, say 1 over x would be considered a rational function. But x over 1, for example, if you simplify this, it's just x. So that's just a polynomial. Okay. So to guarantee that you have a rational function after the expression or the rational function is reduced, you need to have at least one term with an x in the denominator. Otherwise, it'll be maybe a polynomial. Okay. So again, typically your rational functions could have a horizontal, vertical asymptote, or it could be vertical and a slant. Your rational function will never have both a horizontal and a slant. It'll have one or the other. You won't always have a vertical asymptote. It just depends on the function. For example, I could have an example. Let's say this is the axis here, and I could have a one that say goes something like this, where this point is 0.02, and then the graph approaches the x-axis this way, approaches the x-axis this way, on the left side also. You have a horizontal asymptote, and there's no vertical. Okay. So let's look at the one that I have here. Again, if the degree of the numerator, okay, this has to be in simplified form, so I factored it out so you can see. Okay, there's no common factor, so there's nothing I can cancel out here. If the degree of the numerator is 1 more than the degree of the denominator, okay, degree of the numerator is 2, the degree of the denominator is 1 because it's x to the first. So in this case, you anticipate a slant asymptote. So what you can do here, you can use synthetic division, or you can use the long division here, and just divide the denominator into the numerator. Okay, so this will be x minus 1. Okay, so we go x into x squared is x, and x times the divisor there will give me here an x squared minus x. Okay, then we subtract. Okay, these cancel out. 0 from minus 6 is minus 6. So the quotient then is x with the remainder of negative 6. So basically that means that this rational function can be written as x minus 6 over x minus 1. Okay. In other words, if I go ahead and combine this, I get the rational function. Okay. So now, the asymptotes are determined by what happens to the function as x goes to infinity. as x gets real large or real small. Well, you can see that if x gets real large, this denominator gets real large. So you're dividing a very large number into, say, a 6, or in this case a -6. So this term right here is going to go to 0. So we can say that as x goes to infinity or negative infinity, this term basically cancels, and the graph approaches the function y equal x. Okay, so basically then I can say that the oblique or the slant asymptote is y equal to x. Okay, and I already have it drawn here. This one right here. So let x be 0, you get 0. So that slant asymptote passes to the point 0, 0. Let x be 1, you get 1. Okay, so say this is a point 1, 1. There it is. Okay, so we don't have a horizontal. The vertical asymptotes are determined by numbers that make the denominator 0, but not the numerator. Okay, so that would be where the give you values where the function is not defined. So you can see that the denominator is 0 at 1, so it's undefined there. So that would give us a vertical asymptote at x equal to 1. Okay, so we go over here on the x-axis 1 unit over, and then I would draw a vertical line. Notice I've drawn the asymptotes with the dotted lines. Okay, generally that's what we do. Okay. Okay. So that's what we have there. We can also note here that when x is equal to 0, okay, we get -6. This cancels out over here, -6 over -1, so we get 6. So the graph passes through the point 0, 6. So that's your y-intercept. Okay, that's your y-intercept. So we go over here, 1, 2, 3, 4, 5. Let's say that's 0, 6. So the graph, I know the graph is going to pass through that point right there. Okay. Now for the x-intercepts, we need to find out basically the zeros of the numerator. Okay, what number makes what value of x makes the numerator 0? You can see it's 3. If I put a 3 there for x, you get 0 over -2. That's going to be 0. Okay, so 3, 0. Okay, so we're trying to find the values that generate y equal to 0. Okay, you can also see that if x is -2, the y value is 0. Okay, so we have the y-intercept and we have 2 x-intercepts. So go over here, say to -2. So okay, -2 over here. And then 3, 0, so this is 1 right there, so this is 2 here, and then we go over, this will be, say, 3 right there. Okay, so this is going to be 3, and over here, that's going to be -2. Okay. Now, what we can do next, and this is, of course, if we're doing it without the calculator, okay, and you're going to be expected to do some of those in some cases, once you show the work, and do it without the calculator. So let's go to the number line here, and we're going to determine, okay, on the number line, what I did here is I plotted the numbers. Let me just clear this for now so you can see it better. Okay. What we're going to do is on the number line, we're going to plot the numbers that make the numerator and the denominator 0. Okay, so we already went through that. -2 is 1, where the numerator is 0. That generates an X-intercept. When it's 3, it's also 0, so I have it there. And then when is the denominator 0? At 1. Okay, so we have the numbers and make the numerator and the denominator 0 in the number line. And then we simply look for the sign of this function. Okay, it's easy to do it by looking at the factored form. So okay, what happens if I pick a number larger than 3, say 4? Put a 4 there. 4 minus 3 is positive. 4 and 2 is positive. 4 minus 1 is positive. I just want to know the sign because I want to know whether this thing is positive or negative. Because if it's positive, that would tell me the graph is above the x-axis. So you can see in here it's going to be positive. So I'm going to put positive right here. Now what happens between 1 and 3? Okay, let's put a number. Let's put 1. Well, let's pick a 2 between 1 and 3. So if I put a 2 there, this factor is negative. 2 and 2, that's positive. 2 minus 1 is positive. So only one factor is negative. All the others are positive. So that would make the whole thing then negative. So I have that. Okay, now what happens between negative 2 and 1? Okay, what's the sign? So let's pick 0. Put a 0 there, put a 0 there, 0 there. Okay, so I get a negative here. This will be positive over a negative. Okay, so that'll give me a positive. So in between negative 2 and 1, the graph is, the value of the function is positive. Again, the positive tells me the graph is above the x-axis in that interval. Negative tells me it's below. To the left of negative 2, let's pick a negative 3. So put a negative 3 here. This factor will be negative. Here, x minus 3. Negative 3 and 2, that'll be negative. Okay. Got a negative times a negative on top. That's positive. And then a negative 3 there. That'll make this negative. Positive divided by a negative is negative. So in here it's negative. Okay. Now, let's go back. And I put the information here. So what did we say? We had the graph, the y-intercept at 0, 6. I'm just going to mark this right there, and that'll be 0, 6. That was the y-intercept. Okay, and then right there, this is 1. Remember, 3, 0 was an x-intercept, so it was 1, 2, 3. Okay, so at 3, 0 we have a x-intercept. Okay, and then at negative 2 we have another one, so we go over here, so that's 1, 2, that's negative 2. Okay, and those are the only points I'm going to use. Okay, and then I'm going to use the fact that I know that x equal 1, this line right here is a vertical asymptote, and this line right here, y equal x, that's a slant or oblique asymptote. And then we know then that the graph approaches the asymptote. Generally it doesn't touch. It could touch a horizontal or slant. It's never going to touch a vertical asymptote because that's where the graph is undefined. So always make sure you never have the graph crossing the vertical asymptote. In this case we have 1. Sometimes you can have, say, 2 or more depending. Okay, so now we just use a little common sense and use the number line. Okay, so let's start on the far right. You can start anywhere you want, but I like to start on the far right, or far left, but far right here. To the left of 3, I have a positive. That tells me the graph is above the x-axis to the right of 3. Okay, so here I'm going to go up because I have a slant asymptote, and I know the graph has to approach it. So it's going to go something like that. Okay, what happens between 1 and 3? Okay, this interval here. Well, I have a negative, so that tells me the graph has to come down. But because I have a vertical asymptote, then I draw the graph so that it approaches the vertical asymptote. So it goes something like that. Again, this is just a rough sketch without plotting any other points. If you want to be a little bit more accurate, you can plot some other points. Okay, pick, say, 4, and you get a point up there somewhere. Or pick a positive 2, you get a point down here somewhere. Okay. Now, what happens between negative 2 and 1? And to look at the number line, negative 2 and 1, that's a positive. So, okay, between here and here, I have a positive, so the graph has to pass through this point and has to go up. And I know it passes through 0, 6 because that's a y-intercept. So I draw the graph then, so it goes up like that through that point, and then it approaches the vertical asymptote. To the left of -2, I have the negative, so that tells me the graph has to come down below the x-axis. And then because I have the slant asymptote there, then I draw it so it approaches the slant asymptote. So you get something that looks like that. Okay. So again, I'm looking at, in this case, at rational functions here that have a slant asymptote, and that's going to occur typically when you have the degree of the numerator 1 more than the degree of the denominator. Okay, this is 2 and this is 1. And you can get the slant asymptote by simply dividing the denominator into the numerator. And shortcut is drop the remainder and then take the quotient. So in my case, when I divided this out long division, you can use synthetic division also. But if you use long division, you get the quotient is x, and the remainder is -6. So just ignore the -6 and you get y equal x, and that's how I got this right here. And then the vertical asymptotes are generated from numbers that make the denominator 0. In this case, so there's only one factor, x minus 1. So 1, x equal 1 is your vertical asymptote. Okay. Again, if the degree of the numerator and denominator are the same, you could have possibly a horizontal, or if the degree of the numerator is less, again, you will have a horizontal. Okay, so this is kind of what it looks like. Again, a rough sketch. Now, if I wanted to verify it on the calculator for you, for example, then I would come over here, and typically most calculators, some will show you the slant. The 89, for example, will show you the slant asymptote, but generally they don't show the vertical. So if I turn this on here and go to y equals, okay, I have the function already entered there, x squared minus x minus 6 over x minus 1. If I hit graph, that's what the calculator gives you. Okay, so obviously again, they don't show you the slant asymptote, which is this line right here through the origin right there, and then your vertical comes at x equal 1 coming down just like this. Okay, and this point right here is the point 0.06. The graph goes up here and then it approaches that vertical asymptote. Okay, you can see again, mine's a little bit messy here, but that's what you can see. They're pretty close to the same thing. And remember, all I did here is just plotted the intercepts, the x and the y intercepts, and just using this number line right here to get the graph. Okay, so if you have to do a graph like this in class and the instructor doesn't let you use the calculator, this is one way to do it. Okay, so see you next time with another video. Thanks for watching.